So, jetzt haben wir, glaube ich, länger keinen mehr gehabt, der noch nachgekommen ist. Dann würde ich sagen, legen wir los. Also herzlich willkommen zur mündlichen Prüfung im Promotionsverfahren von Herrn Michael Häußler. Mein Name ist Markus Zimmermann, ich bin Leiter des Lehrstuhls für Produktentwicklung und Leichtbau und ich heiße auch willkommen die Prüfungskommission, bestehend aus dem Herrn Rixen und dem Kollegen Seber, beide TU München. Gut, wir haben jetzt einen Vortrag zu Beginn von 20 Minuten und danach werden wir mit der mündlichen Prüfung weitermachen. Auf den Vortrag freue ich mich schon sehr. Ich kenne das Thema ein bisschen. Herr Häußler, ich darf Sie bitten, das Wort zu übernehmen und erzählen Sie uns bitte von Ihrer Dissertation.
Ja, danke schön, Herr Zimmermann. Ich werde jetzt auch gleich auf Englisch rüberwechseln. Ich hoffe, das ist für alle okay, damit es auch alle verstehen. So, thanks for the kind introduction. And welcome to my PhD defense talk, which is about modular sound and vibration engineering. And if you look at the background picture here, I think this nicely conveys what we want our cars to be like. So they should be our comfort zone in our safe space, so we can enjoy the ride, and eventually also our kids can sleep. And what we don't want is to be disturbed by any background noise of machines running in the car. So my talk is about the sound engineering that is required to design cars towards this goal. And therefore, I'll give you a quick introduction by showing you a current electric vehicle, which is in production. So what you can see down here is the battery, a lot of cables, the car body, and this component here in the middle is called the electric climate compressor. And these components can be very noisy, especially when they cool or heat the battery cells. And I'm going to give you a quick listening example of that now.
Hi, I'm at the supercharger in Elverum, and right now I'm getting about 100 kilowatts. And you hear this noise? This is completely normal because we are receiving so much energy so fast. So the compressor are working on high gear. You can actually feel the heat coming out here. Yeah.
All right. So this YouTuber is perfectly right. Unfortunately, the cell heating rate goes up quadratically with the current when charging or discharging the batteries. So we kind of need this component in every vehicle. And now the art of acoustic engineering is really to think about how do we connect this thing to the vehicle and isolate the sound in order to not hear it. But it even goes further because you cannot just add excess material, which is not required. So if you think about acoustic countermeasures, you could think about intermediate masses and sound insulation capsules, but they all add weight, costs, and excess resources that you need. And if you then think about the yearly production rates of popular vehicles, you can see that this is actually an important point to consider and to get your models right for getting a good design. And to make things concrete, I'm showing you here the setup of the electric prototype, which I'm going to show you at the very end in my PhD thesis. So this was a climate compressor that was isolated from the vehicle with a double isolation. So you've got two sets of rubber bushings and an intermediate mass called a carrier here in between. And what you really then want to do is you want to take individual component models, which you just model with the most convenient approach to model them, virtually couple them together in order to predict the vibration and sound transfer path all the way up to the driver's ear. And then you also need an independent description of the source excitation of this component, which is in this case the compressor. So this both transfers sound and vibration over the structural connection points and also over the airborne path by radiating directly from its housing. And then you want to do some signal processing in order to listen to your design that you have now virtually in your computer. And this is what I'm going to explain in more detail now. So let's jump into substructuring. Imagine you've got a model of your structure A and a structure B, and you want to couple them. Well, there's really only two coupling conditions. So you've got the vibrations and forces acting on the interface on structure A and structure B. And if you want to couple them, you got to ensure two coupling conditions, which is first that they do the same vibrations on the interface, and that these forces acting here on the interface, that they are equal in magnitude, but opposite with sign. So this is really just Aktio ist Reaktio from Mr. Newton. So this is not so difficult, but the question is really, how do I get a good model of any substructure? And the first thing that comes into mind is a numerical model. And you can obtain a description of your components by any standard finite element or multi-body simulation package. As I've shown here in this example with finite element model, you can, for example, take your connection points at the interfaces and then place one of these rigid elements here. These are like a virtual point here in the middle of the connection point with 6 degrees of freedom where you can enforce the coupling conditions with the next structure. What you can also do if you have a complex structure, which is too complex and it takes you too long to get an accurate numerical model, or you just don't have a model, you could take an experimental model. So this is rather straightforward at first when you think about, well, let's just take vibration sensors and force sensors and measure the relation between forces and vibrations at these interface points. But in order to really have a description that you can couple to other models, we use something called the virtual point transformation, which is really key to most of the things I'm showing here. So what you do here is that you equip your connection points with a couple of sensors. You perform a few impacts with your force sensor equipped impact hammer, and then you measure a transfer function. And by knowing the geometry and position of your impacts and sensors, you can then use transformation matrices to transform your measurements to a description in a virtual point here in the middle of this connection point. And this is then compatible again, for example, with your finite element model. So the real catch and what I want to stress here is that data quality is crucial. So you want to do all the checks that you have at your disposal for checking that you have an accurate experimental model. And we've learned kind of the hard way what can go wrong in these experimental models. But other than that, this is a really handy modeling approach for a substructure and rather quick if the structure is already existing. What's even quicker, if you have a really simple structure in your transfer path and you can model it as a rigid body, is to go ahead and just model it as a rigid body. So imagine like one of these crosses here, they're basically rigid in your frequency range of interest. And you just define a general coupling point on this cross. And we formulated the equations such that they nicely fit into this substructuring framework. The only thing which I wanted to stress here is that it's important to also consider the added mass of these sensors. And if you do this, you can get an almost perfect match between your rigid body model and a reference measurement. So that turned out to be very handy for some simple structures or these crosses that you can use for testing. And then as last, you often have rubber isolators in your sound transmission path. And here it wasn't exactly clear to us how to model this at the beginning of my research project, because you have quite a few challenges with these rubber models. And one approach that we found in literature was called inverse substructuring. And here the idea is quite simple. So imagine you take two of these crosses, which I've just shown you, and you attach them to your rubber bushing, perform your measurements on these crosses, and transform them to two of these virtual points with 6 degrees of freedom on either coupling point of the rubber bushing. So you end up with a dynamic stiffness matrix of this assembly. And then inverse substructuring uses the fact that these off-diagonal terms here are only a property of the connection element, which is the rubber isolator. And what you then do in order to come up with a model for this full isolator is that you assume a simple topology and a negligible mass of the rubber isolator. So to make things really simple, if you just think of two masses between a spring and you look at this dynamic stiffness matrix, you can see minus the stiffness here on the off diagonal, and then you can recreate this on diagonal term, which you want to have. So basically, you make this simple topology, degree of freedom to degree of freedom connection assumption and negligible mass, and then you build your rubber isolator model from that. Now, if you look at these off-diagonal terms, which are something that you can validate with measurements on a hydropulse measurement machine, you can see that you get a pretty accurate match in the determined stiffnesses. And what is also interesting is that towards higher frequencies, you can also see these dynamic stiffening and weakening effects again, which are due to internal continuum resonances in the rubber bushing, and they cause problems sometimes with gearbox whining and electric motor sound. And this is what we've seen already in other projects. All right, but as I said, you make quite a few assumptions here. So why don't you just go ahead and use a full decoupling? As I've just said, we can model these crosses quite easily as rigid bodies, and we can then just decouple them from the measurement that we took on the coupled assembly. And then we get the rubber bushing model, and we have no assumptions other than linearity. And if you do that, then you can also look at these on-diagonal terms and compare them to the off-diagonal terms, which should be equal under the assumptions of inverse substructuring. But you can clearly see that this is only true up to a upper frequency limit, because after that, the mass effects of the rubber bushing kick in. But the important point is really to see how these models perform in substructuring. So what we did is that we've set up a small validation measurement where we used these bushing models for predicting the FRF of a new assembly. And you can see here that with this decoupling approach, you get an almost perfect match in your prediction with the reference measurement. And here, with this inverse substructuring approach, you can see only from the list that we have tested quite a few different variants of this method, but you can still never get it quite right. So we were very happy with these results, and we use them a lot also in our daily practice and in the rest of this thesis. So with these models, we've covered quite a few of the challenges. So we include these the frequency-dependent stiffness and internal resonances in the bushing. We kind of got rid of the necessity to have a material model because we just took the component as it is and modeled it. And the only thing that's missing now is nonlinear effects, but there is a lot to come by bright people working currently at the chair, also in this direction. Good. But if we look again at the high picture here, or the high over picture, we've got quite a few models at our disposal, which we can couple to each other in order to simulate a complex transfer path in a vehicle. So the last thing which is now missing is something how we model the source excitation. And this is what I'm going to talk about now. So what you have in your vehicle, you've got your source A, and it has some internal forces which are exciting the system, and these vibrations are transferred with the transfer function of the full assembly AB to sound and vibrations on your receiver. The problem is that these internal forces are first of all complex to model, so you've got maybe unknown parameters, or it's a supplier part where you don't have a model of. And even if you take the component on a test bench, you need some sort of data processing to make these results transferable to what you're going to have in the final vehicle. So what you really want to have is an abstract quantity to describe the source excitation independently of the test bench. And this is where blocked forces come in. And I'm going to explain you in a nutshell what these blocked forces are. So blocked forces, if you really think about them, these are the forces that if your source is in operation, so this is running this component, and if you would apply the blocked forces on the interface here, then they would block any vibration on the interface. So the interface is completely blocked, and therefore you would not have any vibration and sound left on the receiver. So this is really just like an active noise cancellation. This is, of course, not what we really do, but it helps in thinking about why these blocked forces work. So imagine, since we model our system as a linear system, we have our source in operation, and then imagine we just add these blocked forces with a positive and a negative sign here on the interface. So we basically didn't modify the original situation. We've just added 0 to the equation. But we know from the picture before that these two components cancel each other out on the receiver. So these two contributions are canceled on the receiver, and we see that we can simulate all sound and vibrations here on the receiver with just, if you want to be accurate, the negative blocked forces. Okay, so that helps in thinking why they work, but of course we can never build a really rigid test bench. So what you do in practice is that you say, okay, I'm going to attach my source to a flexible test bench. I'm going to record the vibrations on this test bench, and then inversely compute what forces would have caused this vibration. All right. So now we have the source description and our transfer path potentially from substructuring, and we want to make predictions for what happens at the driver's ear and also listen to that. So therefore, we've got to look at some of the signal processing that's involved in this whole approach. So what we typically do is that we record the vibration levels on the test bench. We chop that into individual time blocks, transform these into the frequency domain. There we do our computation of the blocked forces, make our predictions for what's happening in the driver's cabin. And then we get our results for a sound pressure in the driver's cabin also in these frequency blocks. And for listening to them, we need to go back to the time domain. And the simplest approach is to just take these frequency blocks, transform them back to the time domain, and stitch them back together. And this is called cyclic convolution. But if we create the sound files like this, you can see a problem since we violate an assumption of the Fourier transform, namely that the signal is perfectly repeating in each block. And if you listen to the sound files that you create such, you can hear that this is not really what you want. So you can hear these jumps here at the time block bounds. So we have tested quite a few methods of how you could get rid of this. One that I'm going to show you here, which I think is generally well applicable, is that you say, okay, I'm going to take all the operations that I have in the frequency domain for coming up with my prediction at the driver's ear and cast that into one transmissibility matrix. And then I'm going to transform this to the time domain, this transmissibility matrix, to a FIR filter. And then I'm directly taking my recorded time signal from the test bench and convoluting it with this transmissibility matrix. And therefore, I end up with my sound predictions directly in the time domain to which I can listen. And here you really don't make any assumptions about the nature of this excitation signal other than that you have linear systems. And if you listen to that, you can hear that you got rid of these artifacts. All right, so now we know how to model our source and then listen to the predictions, but there's a last topic in order to have clean predictions, and this is the field of regularization. And regularization is really concerned with this amplification of measurement noise that you have in this inverse computation of the force. So imagine this very simple system of just a spring, and you measure the vibration here at this point, and you want to infer what the force was that caused this vibration. But unfortunately, you also have some measurement noise in your vibration signal, so an error, E, U. So the estimate that you have of this force is going to be made up of two components. First, the true force, which you want to identify, and then also this error component. And this is no problem as long as this error component is small compared to the true vibration. But imagine you've got a very stiff system with a very stiff spring. Well, then say your force stays constant, but the error or the measurement noise in your vibration signal is typically independent of the overall level. So this error component here in your computed forces increases quite a bit. And this can give problems which are actually audible in your predictions. And what regularization is doing, it's filtering the forces in these stiff directions. And we've tested multiple methods for using this, and especially one where you use the signal to noise ratio for determining the filter factors turned out to work very well for the compressor. So let's listen to a validation measurement on a test bench. All right, now let's listen to the regularized prediction. Now that sounds very similar to the validation measurement, but now let's listen to the standard inversion without regularization. So here you can hear a lot of background noise and rumbling, and this is really at the resonance frequencies of your receiver, this sound pollution that you hear. And what really happens here is that you've basically amplified your measurement noise twice. You have once amplified it in the stiff directions of your test bench, and then just by chance, because you're unlucky, you hit a resonance frequency of your new receiver and amplify the measurement noise again. And this can, yield spoiled sound predictions. All right. So this was insightful and good. And then the last thing, I'm going to go over this very quickly, is since the E-compressor is radiating sound also directly to the air from its housing, we described this transfer path with equivalent monopoles. So basically what you do is you hang up your source component, which is surrounded by many microphones, and then you also inversely compute an equivalent source quantity describing this airborne path. Okay, and now if we look at this, we're really finished with the source description, and together with substructuring, we can now really go to the fun part where you use this in a virtual prototyping approach. So here again is this design of a electric vehicle prototype where the compressor is doubly isolated from the vehicle. And I'm now going to go quickly into the individual models that we used for modeling this transfer path. So the compressor was described just as a rigid body. So I'm showing this here in a small video. So you can see here that you have these 4 connection points where the compressor is attached to rubber bushings, but in essence, this is just a rigid body. The rubber isolators are described with the method that I've just explained you before. These are 4 different variants for the potential rubber isolators that we could use with different materials. You can see here what is very interesting, one of these internal anti-resonances, where one rubber bushing, which is supposed to be the most flexible one, is actually stiffer than all the others. For this intermediate mass, we used a finite element model. The second stage of rubber isolators were described with just the same approach as the previous ones. And for the vehicle, we used an experimental model. So what you can see here is a view in the engine compartment where you have these 3 coupling points where you couple your suspension mechanism. And we've attached these crosses here for being able to excite them properly. And what you can also see here is an automatic hammer for exciting. And then we've also measured the transfer path to sound pressures and microphones in the vehicle. The only thing which is noteworthy to mention here is that you need to consider the added mass of these crosses, because especially at higher frequencies, if you don't decouple this mass, then you get quite different and actually wrong transfer functions in your model. All right. So with all these components, and you can see that this is actually quite flexible. You can choose whatever approach fits your design best for the individual components. And now we can make predictions for what the transfer function all the way from the compressor to the driver's ear is going to look like. And we've tested this design physically. And what you see here is a validation measurement for an input on the compressor and an output on this intermediate mass. And what you can see here is that the substructuring result fits the reference measurement quite good. Only here it's higher frequencies, and I've also plotted the coherence of the reference measurement down here. You can see that, well, you cannot apply enough input energy to your system to really measure this transfer function. And with substructuring, since you've modeled all your components individually or measured them with a good signal to noise ratio, you can actually make predictions at frequency ranges which were previously not even possible to obtain them, even if you have a full prototype. So that was very interesting. So here you can see a similar thing for an input on the carrier and an output on the vehicle subframe. And here you can see an input on the carrier and an output on the microphone in the driver's cabin. And here you can really see that it's almost impossible already to get a good signal to noise ratio. And yeah, so that was very rewarding. And then you can, with your source description, go ahead and make noise predictions for what's going to happen inside of the driver's cabin. So what I'm showing here is a low speed of the compressor and a high speed of the compressor. And you can see at lower speeds that the, if we took a validation measurement, that this one is almost entirely dominated by the structure-borne sound. So SB TPA is the structure-borne TPA path. Now, if you go to if you go to higher speeds, you can see that the interior sound was mostly dominated by the airborne transfer path, and the structure-borne path with this double isolation was, completely in isolation already. And also, if you listen to the interior sound, you can hear this. So that's the sound from within the vehicle, and this is the prediction for the airborne sound now. Right. So the learning in this case was, well, the structure-borne isolation is good, maybe even too good, and we would like to find a less complex design, which is using less material, is not that heavy, and that the airborne path is actually dominant and really sticking out of the noise floor. And you might want to consider wrapping your E-compressor into a sound insulation capsule. Okay, and now that you have this flexible model, well, then it's natural to apply some virtual design modifications, like modifying the finite element model of your carrier here, or just changing the rubber bushing stiffnesses, or play around with your design and see what happens if you leave out bushings. And the last thing which we did in the last chapter, which lends itself naturally, is that you parameterize your individual models and then let an optimization algorithm find the optimal isolation mechanism for your design. And what we also see in industry a lot now is that you use the description of your component and these blocked forces to agree on targets with your suppliers. All right. And with that, I hope that I've given you a good overview of what I did in very brief time. So this was 5 years of work. Thank you very much, everyone, also for helping me in any way. And I hope to see you in person again soon. Thanks.